Alright, you guys, today we're going to look a little bit more at fractals, and we're going to look at exponents and fractions when it comes to fractals. So these are some of the things we're going to learn today with this video. And then in class, we're going to review some famous fractal diagrams, some things you've already looked at. We're going to learn a new fractal called the Koch curve. And we're also going to learn the concept of a curve created from line segments when it comes to that Koch curve. Right, first of all, some things you already know, right? This is called the Mandelbrot set. Okay? So we have this fractal that looks like this pattern where it's kind of this ball or this bulbous pattern, and it's actually made from a fractal called the Mandelbrot set. And these are other examples of the Mandelbrot set. Again, if you recall, these patterns are made from feeding an answer to an equation in the beginning over and over and over again to get this pattern. Now remember what this one is called? It's not that circular, then not that circular ball pattern, but it's this swirling pattern called the Julia set. Let's look at a couple more of those. Again, these are also examples of the Julia set. Let's take a look. Which would this one be? You see that pattern in the middle, so that's going to be the Mandelbrot set. The swirling pattern, if you even look at the smaller pieces in the larger picture, that's going to be a Julia set. Again, the swirling pattern, it kind of looks like a seashell, right? Called a Julia set. And then this is one that we looked at. This again is called your Sierpinski triangle. Now recall that recursion rule for the Sierpinski triangle. Your Sierpinski triangle recursion rule, the S just in this case stands for Sierpinski, is we are going to create new triangles by connecting the midpoints. It's going to be a little bit messy. So by connecting the midpoints of the what? Not of all the triangles, but just of the upward facing triangles, right? So if we always connect the midpoints of the upward facing triangles, we're going to get this pattern called the Sierpinski triangle. So connect the midpoints of the upward facing triangle. That's our recursion rule. Well, let's take a look at a different one. This is a Koch curve. With a Koch curve, we're going to start with this one segment. So that's the first part. Now go ahead and do this in your notebook. I want to see a Koch curve in your notebook. Try to follow the steps. We're going to break that segment into thirds. You can kind of see how I've broken this segment down into thirds. Right? From there, I'm going to take those thirds and bump up the middle segment and add a segment to connect it. So I've taken that middle piece, bumped it up, and now I'm adding a segment to connect. Okay, so that's what I have so far. Okay, now from here, we're going to do something else. We're going to repeat steps 2 and 3. So I'm going to show you. So again, what did I do? Whoops, not that one. Let's try this one. I'm going to bump up each middle segment. Right? This is not going to be perfect because I'm just kind of doing this as I go. So I bumped up each middle segment. And now what do I need to do? I need to connect all the pieces, right? So now I have kind of this star shape. Now again, this is going to be an imperfect fractal because I'm just freehanding. But I get kind of this star shape starting in the middle, right? So if I keep doing that, if I keep breaking each piece into thirds, bumping the middle piece up and connecting, that's my Koch curve. Right, so you get a better image of it here. We got this far. It's kind of step 2. As you can see here, so stage 1, stage 2, stage 3, stage 4, and stage 5. Notice it starts looking like this sort of snowflake, right? Okay, so how does the Koch curve then become the Koch snowflake? So I have stage 1 now is a triangle rather than just a line segment, but I'm really doing the same thing. Okay, so you can see the steps to make this a snowflake instead. So I'm taking each of these sides of the triangle and doing the exact same thing that we did a minute ago. So this would be one line segment split up into thirds, another line segment split up into thirds, and so on. So we get all of that. Okay, so now we have this Koch snowflake. Pretty cool. Let's go back to this Koch curve. So let's take a look at the stages that we did here. We had stage 0, stage 1, stage 2, where we started to get this kind of star pattern in the middle. Let's look at how that relates to our fractions. You know what, I'm going to go ahead and erase all this. Let's take a look at how this relates to fractions. So stage 0, right here is stage 0. I have one segment. The length of that segment is one whole piece. So the total length is still just one whole piece. Well, if I look at stage 1, which is right here, right, how many segments do I have? I now have 1, 2, 3, 4 segments, right? Oops. So I have 4 segments. The length of each segment now, if we think about this, we really would split this into thirds, right? So this first segment right here is 1/3. And these are all going to be equal in length. So each of these segments is 1/3. Right? So now I have the length of one segment is 1/3. That's 1/3 of this first stage. What's my total length? Well, there are 4 segments. Each is 1/3. So 4 times 1/3. It's going to be 4/3, right? If I multiply my numerators and multiply by denominators, I have 4/3. Okay, let's look at stage 2. What do you think is going to happen here? How many segments do I have? 1, 2, 3, 4, right? 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16. Well, I'm going to just stop for a second. If I look back at the previous stage, I had 4. Now I have 16. Remember, 16 can also be written as 4 squared. Okay? So we have 4 to the first power here. And we have 4 squared for our stage 2. Now, what's the length of each segment this time? Well, this time I have in this piece, so I take a look at this piece. Remember, this was 1/3, right? If I look back up here, that was 1/3. So this whole thing is 1/3. Now, each of these pieces is going to be 1/3 of that. Because remember, I broke it into 3 equal parts. So that's going to be 1/3. So now I have 1/3 of 1/3. Remember, of in math means times. So now each of those smaller pieces is 1/3 of 1/3. It's 1/3 of the segment from before. So there I have the length of one segment is 1/9, right? 1/9, we stick with our pattern here, can also be written as 1/3 squared. Okay, so in the previous step I had 1/3 to the first power. Now I have 1/3 squared. Okay, so what's my total length? Well, I have 16 pieces. Each is 1/9. So 16 times 1/9 is 16/9. Let's take a look, okay? Here I have 4 to the first and 3 to the first. Over here I have, in my next stage, 4 squared over 3 squared. So really it looks like all I'm doing from stage to stage is multiplying by that value again. So 4 to the first, 4 squared. Now I would say at stage 3 that I would probably have, if we follow that pattern, 4 cubed. And in my denominator, if I go to stage 3, I'd have 3 cubed. Let's take a look at that a little bit further. Okay. Oops, let's erase that. So at stage 3, what is the best estimate of the total length? Now if we think about what we just said, stage 2 I had 4 squared over 3 squared, right? So it looks like at stage 3 I'd have 4 cubed over 3 cubed. Simplify that. 4 times 4 is 16, times 4 is 64. 3 times 3 times 3 is 27. So 64 over 27. Well, that's greater than 2. Right, well, this is less than 2. Can't be less than 2. Can't be 2, because I can fit, 27. I can fit more than 127 into 64. So it can't be exactly 2. More than 2, less than 3. I can fit 2 27s in 64. I can't fit 3 27s in 64. So it's more than 2, but less than 3. So why do we say that the Koch curve can be described as longer yet shorter? Longer yet shorter. If you think about that Koch curve, I started with a line, and then I end up with this, right? Well, it looks kind of to be the same length if I just go from end to end, but if I actually look at the length of each piece, the length in its entirety has gotten longer, right? So that Koch curve has gotten longer. If I stretch out this stage 1 right here, that will be longer than the first. So it's gotten longer. The whole entire thing has gotten longer. Each piece, however, has gotten shorter, right? Each piece is just a third of what that segment was in the first place. Let's take a look at this one. I'm going to skip here to the second part. What is its length at stage 1, just for time's sake? Length at stage 1 is 1. Sorry, length at stage 0 is 1. What's our length at stage 1? Well, if each piece is a third, so it looks again like the Koch curve, I've broken this up into thirds and bumped up 2 pieces, right? So, but they're each of these is a third of that first stage, or stage 0. So I just count my thirds: 1/3, 2/3, 3/3, 4/3, 5/3, 6/3. Well, 6/3 is the same as, I simplify that, 2. My length now at stage 1 is 2. My length at stage 2. Remember from my last Koch curve, I've broken each piece into thirds, right? And each is a third of what it was before. So it's a third of, or times, a third. At stage 1 it was a third, now it's a third of that, so a third of a third. Now each of these is a ninth, just like in the last Koch curve I did. Well, let's try to count those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. Let's see if that makes sense. So there are 36 total pieces. Each piece is 1/9, so I have 36 ninths. What pattern do you notice? If this was 6 to the first power and 3 to the first power, well, it looks like this one is 6 squared. 36 is the same as 6 squared. 9 is the same as 3 squared. So I have 6 squared over 3 squared for that second part. Okay. So if we look at that pattern that we just noticed, 6 to the first, 3 to the first, 6 squared, 3 squared. What's the expression for the length at stage 42? Again, if I follow that pattern, it looks like my exponent matches the stage, right? At stage 1, first power. Stage 2, squared. So at stage 42, I'm going to have 6 to the 42nd power, and excuse the handwriting here, and I'm going to have 3 to the 42nd power. Just using that stage as the exponent. So at stage k, if we just use a variable, I can say at any stage, I have 6 to the k power over 3 to the k power. Right? Not too bad. And we're going to skip the calculator part for now. So we're going to get to work in class with the practice.